Okay, so what did we do last time? So let's do a brief little recap. So recap. From lecture number 5. This is number 6. So we discussed several things, right? We talked about mutually exclusive events. We also discussed what are called independent events, right? So now we have a little bit more terminology. How do we classify certain events? Some are mutually exclusive, some are independent. So the key phrases here. We also discussed the principle of the inclusion-exclusion principle. So that this occurs when you have an overlap of sets or of events. We're trying to figure out the probability of a union of events occurring, and there's an overlap between those events. So mutually exclusive, that means that if you have the intersection of A and B, it's the null set. This implies that A and B are mutually exclusive, or also known as disjoint. So if this, then this. AKA disjoint. And we say that things are independent if what? So if the probability of A intersect B is equal to the probability of A multiplied by probability of B, then A and B are independent. Are A and B are independent events. And we saw that mutually exclusive events are not independent from one another, because if one of them occurs, then the other one can't. So in a sense, they are dependent of each other's occurrence. Independent events means beyond the mathematical relationship is that one event does not affect, or one event doesn't depend upon the occurrence of another event. Okay, and then the inclusion principle includes the fact that if we want to find the probability of A or B happening, so I just want to stress the fact that this here is a union, right? Is a union of sets, but I just want to say that the union is what's called an inclusive OR. It's like saying A or B or both. So a nice diagram here may help. So we're like drawing these sets, these Venn diagrams, right? So if I call this A and I call this B, then this entire thing here, if I shade everything, this would be A or B. And now if you look at it, A or B is including A, B, and everything in between A and B. And therefore, to find the probability of a union, we take the probability of the set A happening, or event A happening, plus the probability of the event B happening, but then subtracting off the intersection of those events or those sets, because we have to account for the overcounting. So these are the special little principles in last lecture that we discussed. Okay, so this is what we spoke about. And I want to start off one of our examples with what we discussed last time, which is rolling two dice, right? So recall example from last class. Recall example of rolling two die. Okay. And I have a question for that scenario. So a pair of dice is rolled. So we have two dice and we roll them. It's a six-sided, and it's a fair six-sided coin. So every side occurs at an equal chance. So what is the probability that the second die singular lands on a higher value than the first? So here we have again rolling two dice, and I want to figure out what's the probability that that the second die has a higher value than the first. So does anybody out there, based upon our previous lecture and what we saw and with the sample space, how would we approach this? By cases? Which cases? So remember, so recall the sample space. Oh yeah, you can do that. You can assume that the first roll gives you a specific number. You can do that, Daisy. First, find out all possibilities that you get from rolling a die twice. Yeah, so recall the sample space, right? Sample space of this probability experiment. And if you guys recall, actually, I'm going to go to see if I can replicate this really quick. So I'm going to copy this. Boom. So this is, hold on, make it smaller. This is the sample space, right? That little chart thing. And let me just take away this. And I don't need this because this is from the previous problem. But what do we want? So this is the sample space, right? And I want that the second roll of the die has to be bigger than the first roll. Do you see how we can enumerate that, or we can see which one of these pairs, these outcomes, satisfies that condition? So first of all, which one of these outcomes do we have the same number up here? And if you see that, it's across this diagonal, right? So each of these rolls here, the first and the second roll, are on the diagonal, correct? And I just want to say, so just note that the sample space, the outcomes are denoted by what's called an ordered pair. So there's an order behind this pair of numbers, namely that this is the first row and then followed by the second row. We already know that the sample space contains 36 possible outcomes, and there's no more and there's no less. The diagonal here indicates that all of these, so I'm going to just draw this using this color here. This means that the first row equals the second row, but that's not what I want. But the reason why I denote this or I care about this is because now I kind of, in a way, separated the sample space into three groups. One of them, the rows are equal, right? The first and second. And if you look above and below, it's like a little triangular region, right? There's like a little triangular region of outcomes here, and then we have a triangular region of another set of outcomes here. Now, we care about the fact that the second row is higher than the first, which means that the second number must be higher than the first. And if you notice, everything in here, the second row, the second number is always going to be bigger than the number that came before it. And you look at it on the other perspective, the opposite is true. The first row and for every pair here is higher than the second row. So in reality, all I really care about is this. So this is my, whoa. Sometimes it doesn't really do what I want it to do. I want to create, there we go, a triangle. And so this is my desired outcome. This is my desired event, right? I want the second row being higher than the first. And so the probability that this happens, so now we just count the probability that the first row, I should say the second row, is bigger than the first row. Well, just count. How many do I have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. I got 15 possibilities out of a total of 36. And if I want to reduce this, divide by 3, and I get 5 over 12. And this is my probability. Boom. So the probability of this happening when you roll a die is 5 out of 12. But I just want to stress the fact that this problem became a little much more simple in the moment I was able to enumerate all the possibilities, and I was able to group the outcomes in my sample space to, these specific sets where one of them is exactly what I want. And so this technique of separating your sample space in a very clean fashion is very helpful to find probabilities of certain events occurring. And we'll see more of that shortly. Okay, so we talked about that. And then let's see. Yes, so then I want to go on to this next example. So this is a little bit of, this is an example using the principle of exclusion and inclusion. Okay, so we have 60% of students at a school wears neither a ring nor a necklace. 20% where a ring, where a ring and 30% where a necklace. If a student is chosen at random, is randomly chosen, find the following probabilities. So the first one is, what's the probability that a student wears a ring or a necklace? Should it not be? What do you mean? What do you mean hijab? Should it not be 20% wear necklace? I see what you're saying. So I know 60 plus 20 plus 30 does indeed give you 110%. Mm-hmm. And so this is where I stressed the fact earlier in the recap that this is an inclusive or, right? So when you see these words, I know sometimes people think of or and they say plus, it's that kind of association, but you have to be a little bit more careful with that. This or, so, and hopefully with these kind of problems, and if you see your textbook, the Ross textbook, they go into very, for each chapter, there's like tons of examples, and sometimes they go like way deep into like very advanced techniques of probability. But the idea is that there's a lot of examples to go through. So the more examples of problems that you see, the better, your understanding of how to approach problems will be. So this or, don't take it lightly. Okay. This could be people that wear rings only, or necklaces only, or people who wear both a ring and a necklace. That can happen. And so what is always good is to always define your events and do it in a clear fashion. So we're going to do this. Let A be the event, right? Event that a student wears a ring. So that's a set. That's a certain event that the student wears a ring. And then B is the event that a student wears a necklace. So you see what we're doing? We are setting a clear label to what these two events are. So we labeled them, we identify this as one event, and we identify this as another event. So in reality, what are we looking for? Our goal is to do what? Our goal, we want to find the probability of A union B. That's what we want to find. So first thing we do is define what our events are. And what also helps a lot in these kind of problems is drawing again. So we're going to draw this rectangle representing the sample space of this probability experiment. We're going to define the two circles as being the two events that we're concerned with, A and B, right? Where A is the people who wear rings, and B is the event that they wear necklaces. And I want to find the probability that they don't wear a ring. I mean, that the student wears a ring or a necklace, right? So then what do we know? We know that the probability of A union B is equal to the probability of A plus the probability of B minus the probability of A and B, the intersection, right? Now let's go back to what they give us. So this is where we have to do the work here. We know 20% wear a ring, 30% wear a necklace. So not only do we know the inclusion-exclusion principle, we know that the probability of A, what's the probability of A happening? 30%. Remember, when we deal with probability, we only deal with numbers that are between 0 and 1. So 20% is the same thing as saying 0.2 as a decimal. So this is 20%, right? And then probability of B is what? 30%. So we know this to be true, but what we don't know is the intersection of these happening. We do not know the probability or the percentage of students that wear both a ring and a necklace. So then you may think, wait a minute, I can't solve this because if I know this, and I'm looking for this, I would have to know this. If I don't know this, then I have two variables and one equation, I can't solve it. But if you look at the first sentence, what does it say? 60% of students wear neither a ring nor a necklace. So what is that? Where is that in this diagram? If you're neither A nor B, then where are you? You're everything that's not in A or B. So this region is the complement of A or B. You see that? So this is the complement. This is the complement of A union B. And how do we denote that? We denote that as A union B, right? And put a complement. Or people sometimes write it this way, A union B, and put a bar over it, right? We use the bar as well, but it's more common to see a C for the complement. But we already know what that is, don't we? The probability of A union B complement is 60%, 0.6. Right? And then don't we know about complementary probability? So remember, see, all this stuff comes together. So remember, the probability of an event happening can be found by 1 minus the probability of its complement. So if 60% of the people don't have neither a ring or necklace, then 40% must have either a ring or a necklace or both. So 1 minus 0.6, that equals 0.4. So did you see that? So the probability of that A or B occurs is 40% of the time. So I was able to figure out part A for I. But this becomes, what I'm trying to stress is this becomes much more clearer the moment I'm able to define my events in a clear fashion, the moment I have a visualization of these events in such a way that it helps me reason out what do I have, and also translating everything that I am given in words, from words to mathematical expressions. And then, of course, utilize very key um, principles that we've learned about the inclusion exclusion principle and also about finding the probabilities of complementary events, which helps us a ton. And so that's part one. And part two would be the obvious other event. We care about what's the probability that a student has a necklace, a ring, and wears a ring and a necklace. So in other words, I want to find a probability that A intersects B, right? The and means intersection in this case, about between this event and this event. So then that's exactly the question that was raised in trying to find the answer to the first part of the problem. So then how would we find this? Once we found part I, we can find part double I. Does anybody have an idea of how we can use the previous work to find this missing piece of information? Yep. We use the very fact what we started with, right? The principle of inclusion and exclusion. So we know that the probability that A or B happens is equal to the probability that A plus the probability that B happens minus the probability that A and B happens. The nice thing is I know this already. This is what, 0.4? I know probability of A is what? 0.3, and the probability of B is what? 0.2, and then I don't know what this is, so I call this X. Right? I call this X. Let me just make sure I got the right, oh no, I switched it up. So this is 2, this is 3, right? 2, 3. And then this equals what? 0.5. This is what? 0.4. And look what this becomes, a very nice, simple, yeah, you do get a negative, Alexandra, in the way you wrote it, but the answer will eventually be a positive, right? So if you solve for this, which is something I think maybe you're happy about that. Wow, this is such an easy algebra problem. So this is negative 0.1 equals negative X, which implies that X is equal to 0.1, which implies that the probability of A intersect B is 0.1. So there's different ways you can manipulate this equation, right? So you can find what the missing quantity is. So you could solve for this equation by putting everything on the other side, negating everything, and you get a different expression. So that's also perfectly fine. But again, this is a key, a very important principle in probability, knowing how to apply this. Sometimes you have 3 of these quantities and you're just looking for the other missing quantity. So how many students, what's the percentage of students that wear a necklace and a ring? It's 10%, right? Because of 0.1. Okay, everyone clear about this? So see, we're becoming a bit more sophisticated with our probability problems and concepts. All right, so that's that. Okay, so now we're gonna go into something next level, next step. All right, so far, I hope, you know, we're in the same boat. We understand probability, we understand sample space, we understand mutually exclusive events, independent events, the application of the principle of inclusion, exclusion, complementary counting, see, complementary probability, and all of these things start to, like, you know, kind of kind of mix and match sometimes within our solving of problems, where we should be able to react appropriately and knowing what technique to use. And the only way that happens is through practice, through experience, through exposure to different sorts of problems. Okay, so the next thing on the horizon is very important in probability, and it's called conditional. Conditional probability. So the key word, the key phrase here is conditional. So now we will be concerned with probabilities of events occurring given that another event occurred. So the moment you hear, so the key phrase that you hear for conditional, the key word that will arise a lot is the phrase, or I should say key phrase. So whenever you see this phrase, your ears should perk up and you should think, oh, conditional probability. When you see the phrase given that, the moment you see given that something happened, conditional probability. So first, I just want to give you the mathematical notation for this, or the definition for this. So a lot of this, these the notational aspect of mathematics has to be clearly translated into words and vice versa. So we say that the probability of A, right? And then we put this slash B. So what does this mean? This is the probability of event A occurring, keyword, key phrase, given that B occurred. Oh, too many C's. And let me just stress, it happened. So we're assuming that the event B, whatever that may be, occurred already. And we want to figure out the probability of A happening given that B occurred. And so then we have this formula, the probability of A intersect B over the probability that B happens. So we've seen this. We know what that is, intersection. We know how to find the probability of B. But now we have this new notation here, probability of A given B. Now this looks kind of weird. So that's why maybe drawing out a picture again might help. It might help. So pictorially, what does that mean? So again, I have two circles. I got A and B. Now I'm going to look at this and say, what's the probability that A happens given that B occurs? So what happens now? Normally, what our samples, when we find a probability of an event, right, we're comparing it to the sample space, the entire thing. So we count the number of things in A, and then we say, hey, how many things are there in the big one? And then we divide, and that's it. But now B becomes our sample space. So conditional probability occurs when your sample space is reduced to an event. So now we can think of this as our sample space under the condition B is reduced. And we reduce it to this now. So now our world, for a moment in time, is only what happened in B. And you see how now this makes a bit more sense, this formula? Because now where is A? What's the only slither piece, the only piece of A that I have? It's here. And this here is A intersect B. And of course, this is B. So the probability that A occurs given that B occurs is this portion here. So first I want to find the probability that this happens divided by the probability that this happens. And then you have the probability of A happening given that B happened. So it's a relative you can think of it as also as a relative probability. It's a probability that in relation to B happening. Okay. So now this is the next step of probability that we're dealing with. So let me just highlight this. Does that make sense, guys? Or am I just speaking in tongues right now? I know it might be a little new, but we'll see with more clarity when we solve problems. And equivalently, so this is kind of nice. This will be very useful too. A useful relationship is that now that we know that the probability of A given B is equal to the intersection of A and B, the probability of the intersection of A and B, divided by the probability of B, we can also, if you solve for A intersect B, we have a new way to find probability of the intersection. And that's equal to the probability of A multiplied by the probability of A given B. This is another way to now find the intersection of two events. Okay, so this might become very useful. And let's see that in action now. Okay, so wait, isn't it PV? Oh yeah, pardon me. That you're right. And so you can also write it this way, or the probability that A intersect B, you could also do it the other way. The probability that A times the probability that B given A. And you can check that yourself. You can check. Because the idea that A and B are used are just, you can use it interchangeably as long as you're consistent with it. So if I change this to B and this is an A, this will be B and A, and this will be A. So it does matter. Yes, it does matter. Yes, it does matter. I'm saying A intersect A bar B or line B means that what's the probability that A occurs given that B occurs? So then if I write this, if I write A, B given A, right? I'm saying what's the probability that B occurs given A occurs? A occurred. Okay, so the order of what letter comes before or after the bar does matter. It does matter. Okay, so let me just give you an example of conditional probability. Again, we have this two fair die thing. Two fair dice are rolled. And then it asks straight off the bat, what is the conditional probability that at least at least one die lands on 6, given that the dice lands on different numbers. Okay. Right. So we're assuming that the two numbers are different. So if you land on a 6, if the first one lands on a 6, which we desire, the other one cannot land on a 6. It would have to be everything else, right? 1, 2, 3, 4, 5. But again, this is an example utilizing conditional probability. So the first thing I always want to recommend you guys to do is to denote your events. So what are your events? To define clearly your events. So let A be the event that what? A die lands on a 6. And then what is B? B is going to be the condition, right? Is that the event that that two dice lands on different numbers. There we go. That's right. This first step may seem like it's not that important, but it's very important because it clears things up. It clears things completely. Now this here is my condition. This is the thing that we're conditioning the probability upon. So let me see, can I, again, drawing this sample space thing is a bit tiresome, right? But it's important though. Eventually, you won't have to rely upon this every single time because now you've gotten comfortable with it. But it's always good to utilize this. So I don't need this part here. So I'm gonna find conditional probability in 2 ways. I'm gonna use the formula and I'm gonna use a more direct method, okay? So using the formula, what do we know about the formula? The probability that A given B happens is what? The probability that A and B happens over the probability that B happens. So we can find these individually. We can find this one first, and then we can find this one first, and then we second, and then we can put them together, and then we solve. We find the answer. So the first thing is the probability that A intersect B happens. What does that mean? That means that a die lands on 6 and both of them land on different numbers. So one of them has to land on 6, either the first one or the second one. It doesn't matter. So what would be A here? What would be A? The event A. What would I have to do? I would have to group certain outcomes here, right? So do you see that this here, if I do this would be A. No, pardon me. This would be A intersect B. Do you guys see that? Because one of them lands on 6 and all of these are different numbers. So that's the intersection of A and B. And what's the probability of this happening? What's the probability of this happening? Just count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So there's 10 ways of this happening out of a total of 36 ways. And you can reduce that. And then what's the second thing we want to find? What's the probability of B happening? Well, what is B? B is the events that they land on different numbers. So we can do that by doing what? Looking at the ways that they get the same numbers. There's 6 of them, right? There's 6 ways to get the same number. So that's the complement of B. So the complement of getting the same numbers is 30 ways to get different numbers, right? So then what's the probability of getting different numbers? 30 out of 36. So I found each probability. So now I could just put this together. 30 over 36, pardon me, this is 10 over 36 divided by 30 over 36. Keep, change, flip, right? When you divide fractions, so the first fraction you keep, you change division to multiplication, and then you flip the second fraction. And when you flip it, what do you notice? 36 goes away. I get 10 over 30, and the result is a third. So a third of them, given that they land on different numbers, a third of the time, the die will land on the 6. Could you also do probability of B is 1 minus probability of? Yes, of course. Be my guest. Be my guest. You can do that as well. You get the same answer, right? It would be 1 minus 6 over 36, which would give you 30 over 36. So if that feels more comfortable for you, then perfectly fine. You can do that as well, but it's not necessary. So does everybody see how we just calculated the probability, the conditional probability of this? And again, what helps a lot is being able to write out all the possibilities and being able to visualize, group them in the event in a way that defines the set that you're looking for. So this is like the formulaic way and by the book. But there's also a little more direct way. It's still the same idea. Nothing has changed. It's just that I avoid calculating probabilities twice. I just can go straight forward. So this is more formulaic way, right? So in the formula, you calculate 2 probabilities, you divide it, you get the probability you're looking for. The more direct way is to do exactly what I mentioned about reducing your sample space. So the moment you're able to identify your condition, the conditional event that you're doing, right? The event that you're conditioning upon. That's the lingo people say. The event that you're conditioning upon. I'm conditioning upon the fact that the 2 dice lands on different numbers. So now my sample space, instead of it being this entire 36 outcomes, now I reduce it to only having those that land on different numbers. And how many of those are there? Well, we just talked about it, right? These 2 groups here, okay, these 2 groups here represent B, my new sample space. In a way, I forget about the ones that have the same numbers on both dies. I forget about that. And I only look at the new sample space. So this is my new sample space, okay? This is my new sample space. Now that this becomes my new sample space, how many things do I have in my new sample space? Well, we just calculated that, didn't we? Aren't there 30 things? So there's 30 outcomes in my new sample space. And within my new sample space, I know that there's what? The ones that have a 6 in them. And how many are those? There's 10. So the probability of A intersect a given B is I can go directly to this number. Do you see that? I don't have to do this, then divide and multiply and cancel out. I can go directly to this given the fact that I viewed B as my new sample space. Does everybody see that? So you can also find the conditional probability that way by visualizing or by considering the conditional event as my new sample space. Does that make sense? Yes, no, maybe so. Yeah, so makes more sense now. Okay, yeah, so there's different ways to think about probability, especially conditional probability. Okay, so we talked about that one. Let's do another one. This is a good one. So this is example number 2 here. This was nice. 3.9. Okay, so consider 3 urns. So we have urn A. So this is, okay, you're gonna be seeing the word urn a lot more now. Okay, they like urns. So in probability, they like flipping coins. They like rolling dice. They like 52 card deck, right? We've been doing that a lot. And now you'll be hearing about urns. Urns, think of it as containers that contain things. And they like containing marbles or balls. That's what they tend to contain in these kind of problems. So we have urn A, urn B, urn C. I love imagining who they are. Yeah, that's that, it's those people that decided to do these problems. It's interesting. Who are those people, right? Like, who are they? So urn A contains 2 white balls and 4 red. Okay. And then, and I'm just saying, consider 3 urns that contain red and white balls. So we have urn B contains 8 white and 4 red, and urn C is 1 white and 3 red. And the problem is this: if one ball is selected from each urn, what is the probability that the ball chosen from urn A is white, given that, okay, conditional probability time, given that what? Exactly 2 white balls are selected. Okay, we have 3 urns, A, B, and C. A has 2 white, 4 red. B has 8 white, 4 red, and urn C has 1 white, 3 red. So that's the breakdown of the colored balls that we have in each urn. And our conditional probability that we're trying to figure out is, what's the probability that I got a white ball out of urn A, given that I select from each urn one of them, right? And exactly 2 of them, so 2 of the 3 balls that I select overall are white. So what's that probability? So again, right? Let. And I'm going to use a different letter instead of A, because urn A is already been used for urn A. So I'm going to use E, okay? So let E be the event that ball from urn A is white. Boom. I defined my event. That's what it is. And then let F be the event that exactly 2 of the 3 balls selected are white. Okay, so we got that. And what do we want to find? What's our goal? Our goal is to find the probability that A is given F, of E given F. And so what do I need to do? I need to find the probability that E intersect F over the probability of F. So for this one, it would be, you would have to directly use the formula. Sometimes you can't just go directly to the correct answer the way you could in the previous example. So this is the first one here. So what's the probability of E intersect F? What does that mean? What does E intersect F mean? So you can also do that. You can also define what that means. So E intersect F means that I want the event that the ball from urn A is white, and at the same time, 2 of the 3 that I get are white. So how do you think we compute this probability? This is probably the more complicated of the examples we've done so far. So it won't always be so clean, right? It won't always be so like clear as the other problems with the 2 dice. You start to see everything so clearly, the outcomes, you can group them, you can circle them, and it's not always that clear. Sometimes you have to think about what that means in the context of our problem here. The intersection is that the ball is white, so it's 11. How do you get 11? Whoa. So again, E intersect F, right? I want the event that the ball from urn A is white, and then I have 2 of the 3 balls being white. Oh, I see how you got 11. Oh, be a little bit more careful. So E intersect F. Let's break that down a bit more. What does that mean? E intersect F. That means that urn A is white, but urn B is what? Red, and urn C is white, or urn A is white, urn B is white, but urn C is red. Do you guys see this? You see how this is like a little bit strange than like a little bit different from the other ones? Because it's not so like to enumerate all the possibilities, it goes a little crazy. We start to go like numbers start to go a little bit more than 36, right? So we want to be more like straightforward and direct in finding what in the world that means. This means that urn A is white, urn B has to be red, and then urn C has to be white if that's the case. So we have 2 white balls out of the 3, and urn A is white. Or the other possibility is that urn A is white, urn B is white, but urn C has to be C. And do you see how this is it? That's it. That's all we can do. And do you also see that these are 2 events that are both mutually exclusive from one another? You can't have one event occurring while the other one also occurs. So these are mutually exclusive. And why is that important to know? Because then we know that to find the probability of this union of events, we just have to add the probability of each event occurring. And don't worry about the overlap because there is no overlap to subtract off of. Okay. So then now the problem becomes, what is the probability of this happening, of urn A being W, urn B being red, and urn C being W? What's this probability? So, this is like events within events within events. So this is one big event, one big event. I'm conditioning E upon F. I'm trying to figure out now the intersection of these 2 events. These are the 2 different events. And within this event, you have smaller events, right? Or like to get earn A being white, that's one event. Earn B being red, that's another mini event. And then earn C being white, that's another mini event. And you clump them together and that becomes one big event. Do you guys see that? And you also should see that these separate events that are clumped together, they're independent of one another. Me selecting something from earn A is not going to affect what I select from earn B. It's not directly affecting it. So that's why they find the probability of this event occurring is the probability that earn A occurs being white. So earn A is white times the probability that earn B is red times the probability that earn C is white. Do you guys see that? Right. So the earn A is what? What is earn A? The probability of me getting a white ball out of earn A is what? 2 out of 6, right? Because I have 6 to choose from. And I have 2 of them that are white. Earn B. How do I get a red ball from earn B? Well, I have 4 red out of 12. So it's 4/12. And then earn C. How do I get a white ball out of earn C? I got 1 out of 4. That's my probability. Do you guys see that? And so then this would be what? 2 times 4 is 8. And then what do we get? 6 times 12 is 72. And so you see how these numbers get pretty big, right? So I get 288. Does everybody see that? And then what's the probability of this other event occurring? Earn A is W. Earn B is W. And earn C is red. Same idea. What's the probability that earn A is white? Probability that earn B is white times the probability that earn C is red. Well, the probability that earn A is white is 2 out of 6. The probability that earn B is white is 8 out of 12. The probability that earn C is red is 3 out of 4. I'm gonna get the same kind of denominator, 288. And this will be 2 times 8 is 16 times 3 is 48. Does everybody see that? So then what is going to be the probability of E union F? So the probability that intersect F is 8 over 288 plus 48 over 288. And when you add this up, you get 56 over 288. So that's what we get for our intersection. Now, what I have to find is the probability of F happening. So that's the first thing we did. Now, the second thing we have to do is the probability of F. But again, what is F? So see, you have to not only define your sets clearly word-wise, using words, you also have to identify what the set is in the context of my problem. So F is what? Exactly 2 to 3 balls are white. So what does that mean? That means that earn A is white, earn B is white, and earn C is red. Or what? Earn A is white, earn B is red, and earn C is white, right? Which is, you're like, wait, we're just doing the same thing again, aren't we? It's the same 2 things, but we have to add one more. Or what? Earn A is red, earn B is white, and earn C is white. Do you see how F includes one more event that is not included in E? Because E is very specific. Ball from earn A must be white. But F alone, if you just consider F alone, that's not a condition. That's not a requirement, because we only care about the fact that 2 of the 3 are white. So I could have that earn A is white, B is white, then red, or I can have white, red, or white, or I can have red, white, white. These things are still going to be in my event F. And what's nice about this is I already calculated these two probabilities. I already did that. So this would be what? This would be 8 over 288 plus 48 over 288. I already know what that is. All I need to really figure out is this last one. What's the probability that earn A is red, earn B is white, and earn C is white? So can anybody tell me what that would be? So again, these are independent events. So if I want earn A to be red and earn B to be white and earn C to be white, then I have to multiply each probability. And what's the probability of getting red from earn A? It's 4 out of 6. And then probability of me getting white and earn B is 8 out of 12. And then earn C being white, again, is 1 out of 4. And so I get what, 32 out of 288. So I get 32 here, right? Out of 288. So now I can find it. Now when I add these up, I get what, 56, right? And then 56 plus 32 is what, 88. So what I did was I found the two probabilities that I needed to find in order to find my final answer. Let me just right. So finally, this was a long one, guys. Not all. I just don't want to scare you guys thinking that, oh, every single probability and conditional probability question will be this long and intensive. I would say this is a medium, close to medium hard. It's not hard, but it's not like simple either. But I would say it's a standard medium conditional probability question. Standard. There's no, it seems like you're doing a lot because you're like, wait, because first of all, this is new for most of you, right? So it may seem like we just went from 0 to 75%, 80% quickly. And the reason why it might be a little more difficult is because now the interpretation of the sets of the events are it's a little different, right? Like it's not as clear as the rolling 2 dice, for example. But the actual like procedure is standard. There's no tricks. It's pretty much exactly what we've been doing. It's just that the context of the problem is a little bit more slippery here, but it's exactly the same thing. I know this, divide. The hard part was to understand what in the world does this mean in the context of this problem. What in the world are these two events in comparison to one another? What in the world would be the probability of one of them happening? They're independent events. But then you start to see, hey, finding this is pretty simple. Finding this is pretty simple. Finding this is pretty simple. Multiplying these things should be straightforward, and so on and so forth. So the important thing is I found this and I found this. And so now what's the probability that E given F occurs? So the probability is E intersect F over the probability of F. That's right, Fernando. So then the probability is what, 56, right? Out of 288, divided by 88 over 288. So do you see how the 288 now, this number, first of all, they're shared both in the numerator and denominator. So that's a good sign. 288 indicates the sample space of my original problem. But now and if you see the mathematics behind it, the 288 becomes irrelevant. The 288 number cancels out. And so I'm left with the ways of getting E and F occurring is 56 different ways, and I get 88 on the bottom. And if you reduce, divide by 8, you get 7 over 11. So the probability that earn A has a white ball being selected, given the fact that you have exactly two white balls out of the three being white, is 7 out of 11. Again, this is more the sophisticated kinds of problems using conditional probability. But if you can follow the logic, and I would recommend going back to this and trying to solve this on your own, if you can follow the logic behind it, then you shouldn't have too much to worry about in terms of finding conditional probability for anything. Okay, so this is going to be your bread and butter, this formula here. Very important. Okay, we have a few more minutes left. And so I want to see if we can do something really quick. So the conditional probability is very apparent when we have what are called two-way tables. So I'm gonna give you a simple example here. So this is when you have, okay, this is less than 125K, which is 1,000. This is more than 125K. And this is less than, why am I drawing this? Less than 125K and more than. So this is an example of two-way tables. You may have seen this before. And the rows here are going to be from, so I'm going to describe what the context of this table is. This is the husband. So according to a survey or a poll, I'm going to put the numbers here, 212, 36, 198, and 54. So according to a poll of 500 married couples, the following information is concerned with their salaries, right? Concerned annual salaries. So we have 500 married couples and we figure out how much they make, okay, each year. It says 36, yeah, okay. And then, for example, one question can be, what is the probability that husband earns less than wife, earns less than 125,000, right? So that's the first question. So what's the probability that the husband earns less than 125,000? So look at the husband columns and how many are less than 125,000. So they have to total these up, right? So these are the totals. You can also do the totals here. So 212. So they all have to add up to a certain number. So 212 plus 196. That's 408. 36 plus 54, 90. So 54, right? Yeah. Oh, pardon me. Yeah, this should be 410. The whole point is that when these numbers add up, they should add up to the same number, 500. And the same thing goes for 36, 248. This is 248. And then 198 plus 54, 252. Okay, so now once I have this, what's the probability that the husband earns less than 125K? Well, how many people are under that category? There's a total of, so I'm gonna call this whole thing A, okay? So what's the probability of this being A? Well, this is 248 out of 500. Whatever that number is, for now, you can leave it that way, or you can write it as a decimal. It's 0.496, so 0.496. And if you want, you can write this as 49.6%. So 49.6% of the husbands from this poll make less than 125K. So that's not that hard, right? And then the question is, with conditional, what is the probability that wife earns more than, and after this example, we're done, given more than 125,000, given that husband earns less. So this is a typical question. This is a typical question. So again, given that, right? Key phrase, given that. So what's the conditional event that the husband makes less than 125,000? And what's the event that we're looking for is that the wife earns more. We can do it two ways. We can do it using the formula, right? So if this is A, if I call this to be A, if I call this as A, then this would be B, right? This would be my this would be my event B. So what am I looking for is the probability that B given A, which is the probability of B intersect A over the probability of A. I can do this individually, find two probabilities and divide. Or in this scenario, I can go directly to what the probability will be using the conditional event as my new sample space. So what's my conditional event? My conditional event is that the husband earns, so this is my conditional event here. Conditional event, this is my new sample space. And this becomes quite straightforward now. So if this is my new sample space, how many people, or what is my sample space consist of now? The husband making less than 125K. How many is that? That's 248. So 248 is my new number on the denominator. You guys see that? And this number would appear if I were to do this individually and divide, and then the 500, which will be the total of the original sample space, would cancel out if you were to do this individually, right? So 248 is my new sample space for the smaller, for the event that has been reduced now. And then of these numbers, what happens? I want the wife to earn more than 125K. So then under this column, which is the husband making less than 125K, how many of the wives make more? Well, it's only 36, right? So then this should be 36 out of 248. And that's how we end this little story of conditional probability. Okay, sorry guys for the going over 5 minutes, but I appreciate your patience, and I'll stop the recording right here.